I still need to post that. I'm going to post it this afternoon. But just so you know, homework 12 is due on Friday of next week, not on Wednesday. And then, after next weekend, the project report, the final project report will be due on Monday. And I noticed that at least one student's already submitted their final project already. So feel free to do it when you've got it done. And if you want me to look over what you've completed, then I'm happy to give you a quick once-over on it just to tell you if I think anything is missing. But are there any questions on the announcements? One other thing I'll mention is that we won't have in-person class meetings next Friday or the Friday after. You're going to begin thinking that I just take Fridays off, but the fact of the matter is there's an advisory board meeting next Friday, and the Friday after that I am kind of just taking off. But next Friday at least I've got a good reason. Actually, we wouldn't even be able to have class in 2 weeks anyways because they're having some conference in the building. So I think a lot of the classes on Friday the 22nd may end up being canceled, not just this one, due to classroom availability. All right, today we are going to finally address underflow gates, a couple of calculation examples. Of course, we looked at an underflow gate in the lab on Wednesday, and we looked at the formulas for predicting what the contraction is, coefficient of discharge, and the ratio of the depths, but we'll put it all together with an example. And here's the first one of those. So we have a canal that's 4.5 meters wide, and we're just looking at this from a side view. So 4.5 meters is that dimension into the page that we don't actually see from this image. The upstream depth, Y1, is 2.7. So 2.7 meters is Y1. So there was pooling that occurred because of this underflow gate, and that's why the water upstream is 2.7 meters. The sluice gate is 1.5 meters. Now this is important to distinguish the fact between the channel width and the width of the gate that's releasing flow. So here's like a dam of a sense, and then there's a gate that is being opened, and so let's see. Yeah, so the water is flowing through here, and this frame has been pulled up out of the way to release the flow. So although the channel itself is 4.3 meters, the width of the gate that's releasing flow is just 1.5 meters. So that's going to be the B value that's used in this formula, is the width of the gate, not the width of the channel. All right, and you can see that the width, the height of the opening, W, is 45 centimeters. So W is 0.45 meters, and the B is 1.5 meters. After contracting, the downstream depth is 27.5. So that's the Y2. So Y2 is the depth after contraction, and it is 0.275 meters. Okay, now one of the things we're going to need to calculate is the coefficient of contraction, because that goes into the discharge coefficient. And so you can see just from this sketch, Y2 equals coefficient of contraction multiplied by the height that the gate is opened. So we have W and Y2, so C sub C will be Y2 divided by W. So for us, that is 0.275 meters divided by 0.45 meters. Okay? So if you have a calculator handy, I think that you'll see that the coefficient of contraction
is that formula only for this problem, or only
No,
for
it's
rectangular gates? Or?
this formula?
The Y2 equals CCW.
It's for the gates where the opening is rectangular. So it could be a radial gate, but even with a radial gate, the opening will be rectangular in shape. Okay, so the coefficient of contraction is 0.611. And from that, we can put it into the formula for the coefficient of discharge. So the C sub D is coefficient of contraction, 0.611 multiplied by the square root of 2.7 meters, which is the upstream depth, divided by 2.7 meters plus 0.275 meters. Okay, so overall, the coefficient of discharge will be 0.5822. And that's just an indicator of how much energy is lost as the water approaches the gate, flows out from underneath it, and otherwise we would just effectively be using the orifice equation. Remember that these openings are pressurized by the depth of flow behind the gate. And so when we say square root of 2GY1, that's giving us the velocity of water as it goes out from underneath the gate. But the coefficient of discharge accounts for the energy losses and the effects of turbulence and so on. So the overall flow rate exiting from the gate, Q, will be coefficient of discharge, so 0.5822. The width of the opening, 1.5 meters. The height that the gate is open, 0.45 meters. And square root of 2G times the upstream depth, 2.7 meters. And that's going to give us the flow rate in cubic meters per second. So if you've got your calculator and can verify, I think what we ought to have here for the flow rate is 2.86 cubic meters per second. So that just kind of shows you how all the pieces fit together for the gate equation. Now, we're not always going to be solving for the flow rate. Sometimes we'll know the flow rate and we'll use the same equation to predict what is going to be the depth upstream of the gate. But here in this first instance, remember that these types of gates are used for flow regulation rather than flow rate estimation. Or a broad-crested weir or a sharp-crested weir, really the purpose of that is just to find out how much the flow rate is that's coming through. This can be used to increase or decrease the flow rate that is making it to a certain location. All right, so that's our first gate example. Now, the location of the hydraulic jump, just to review, that when you close the gate, what it's doing is it's depressing the depth after contraction. As you close the gate further, this is getting smaller. Y1 is getting smaller at the same time that the velocity is increasing. And so what that does is it makes conditions at 1 more supercritical than they were before. And if we think about a momentum depth diagram, if you have a really small upstream depth, then that's going to increase the depth that it jumps to downstream. So to prevent drowning of the hydraulic jump, what we would do is we would find out for the channel that's downstream, what's the normal depth? Just based on the Manning's equation, which reflects the slope, the roughness of the channel, the flow rate, you could find the normal depth and you would select how high you can open up the gate so that your critical depth downstream would be kind of the assessment of whether you can even support a hydraulic jump or whether conditions are going to stay supercritical after the underflow gate. Because if this was a steep channel, like steep enough to support supercritical flow, then the water comes from underneath the underflow gate and it will stay supercritical. It only experiences a hydraulic jump if this is a mild slope. Mild here being a technical term, meaning that the slope is less than the critical slope. So how high you can open up the gate would be the normal depth divided by the coefficient of contraction. So that's just going to tell you the opening that corresponds to the smallest upstream depth that corresponds to jumping to the normal depth downstream. So we're simultaneously using Manning's equation and also the Bellinger momentum equation here. And if you close the gate more, then it'll just cause the jump to run away. But if you open the gate more, then it will cause the hydraulic jump to approach the gate and it will then drown the jump. So ideally what we're saying is that it's finding the normal depth after the hydraulic jump. Okay, so let's put that idea to practice. We've got both an underflow gate and a hydraulic jump in this example. So there's lots of moving pieces in this example. It's an important one. We have the characteristics of the channel downstream, like the slope and the roughness. And we know that we're carrying 25 cubic meters per second. So what we want to see is the depth after the jump is going to be the normal depth. So the first step, you can see I've got these numbered suggestions on how to approach this. The first thing is calculate the normal depth for this rectangular channel. So use Manning's equation, and we have a channel that's 5 meters wide, and the gate is also 5 meters wide. So it's not like the previous example where the gate width was less than the channel width. Here they're one and the same on this next example, both 5 meters. Okay, so calculate the normal depth, and then we're going to set that to the depth after. So here's Bellinger's momentum equation, and I've just, instead of calling it y1 and y2, I've been a little bit more explicit. There's the depth before the jump, so that's the upstream y1 depth, and the y2 after the jump. So here in the Bellinger momentum equation, we're going to set the normal depth equal to the y after, and then so calculate the y before here in step 2. And it says you'll need the critical depth because rather than using the Froude number version of the Bellinger momentum equation, we're going to use the one that has the ratio of the critical depth and the downstream. Because if we look at the other version of the Bellinger momentum equation, let me go to that, it requires the Froude number upstream. And we don't yet know the Froude number upstream. So this formulation of the momentum equation is more useful because we're solving for y before. We're not solving for y after. And that's, we've used the Bellinger momentum equation a couple of times before to find the downstream depth, like the depth after the jump. This is the depth before the jump. Okay, so solve for y before, and then we know that's the depth after contraction. So for a coefficient of contraction, then you can find the height of the opening, W, because remember the contracted depth, y before, multiplied by, or divided by the coefficient of contraction will give you the W. And then the last part would be to put this all into the gate equation to find the depth before. So we're kind of working from the right side backwards. Solving for y after the jump with the Manning's equation, y before using the Bellinger momentum equation for hydraulic jumps, solve for W using the coefficient of contraction, then solve for y1 using the underflow gate equation. Okay, so I'm going to pause for a few minutes, and this is one where I'd really be delighted if you're checking your answers with your classmates, working on this together. I've got the solution, so I'll circulate around and see if you want to verify your intermediate calculations along the way. But here's the step-by-step. Allow me to interrupt for just a moment. I'll let you get back to it, but I just wanted to show a couple of things up at the top. So we are, first of all, establishing the normal depth, because this is a very special case. It's asking how high can you open the gate without drowning the jump. If we open it too high, remember the hydraulic jump will approach the gate and it will drown. And so we want to find out the maximum opening height. And so we're saying it's going to be the normal depth after the jump. And the calculation to determine the normal depth, you can see we've got the flow rate, the N value. For a rectangular channel, the area is simply 5 times the width of the channel. And the wetted perimeter for a rectangular channel is the bottom width of 5 meters plus 2 times the depth, because we've got the channel on either side also contributing to the wetted perimeter. And then that's to the 2/3 power, slope to the 1/2 power. So when you put it into your numerical solver, you should get that the normal depth is 1.78 meters. Okay, so we're going to say 1.78 meters is this y after jump. And we're going to use that, number one, to assess whether this slope is steep or mild. And when we calculate the critical depth, for example, the critical depth is 1.366 meters. And so if the normal depth is greater than the critical depth, then that means the flow conditions under normal circumstances are subcritical and the slope is mild. So we've got subcritical conditions downstream of the gate. That means that it is going to have a hydraulic jump, because the water comes out from beneath the gate at a depth that's less than the critical depth. So this water is going to be going from supercritical flow up to subcritical flow. So there is a hydraulic jump. We know that y after the gate is 1.78 meters. Okay, so what we're going to do for the second part is solve for y before. So the y before is going to use the 1.78 as y after. It's also going to use 1.78 as the y2. That means the depth after the hydraulic jump. And it's going to use the 1.366 that we just calculated for the critical depth here inside the parentheses. Okay, so I'll pause for now. I wanted to give you that. 1.78 is the normal depth, and 1.366 meters is the critical depth. So if you haven't yet solved the normal depth or critical depth on your own, you can just use these values and move on. So now calculate y before using the Bellinger momentum equation. Here, we're using different variable definitions. I'm calling it before jump and after jump, rather than, in the normal momentum equation, it's y1 and y2. But if I said that, it would be confusing, because we also say like y1 and y2 at the gate. So it's hard to keep straight, like what's the perspective here. So that's why I said the before and the after. So the coefficient of contraction is the depth after the water flows out from under the gate and finishes contracting. So here it's y before the gate, before the jump, and then divided by w. So that is, in this problem, the coefficient of contraction is y before jump divided by w. In the previous example, here we had 1 was the upstream and 2 was the downstream from the perspective of the gate. So I just wanted to mention that really what you need to think about the coefficient of contraction is like, where is something contracting here? It's contracting after the gate. So it's the depth after the gate divided by how high the gate is open. Okay, so I'm going to be switching back and forth between the solution and the initial problem just to make a couple of points. We'd already talked about how you calculate the normal depth using Manning's equation, and that is y after the jump. And so y before the jump, we're going to calculate here with the Bellinger momentum equation. So that'll be 1.022 meters, and you'll notice that it's using both the critical depth and the downstream depth in calculating what will be the depth prior to the hydraulic jump. And so that is going to give us this y before the jump. And now the coefficient of contraction is how we can determine w. And so the coefficient of contraction is used to divide y before by the coefficient of contraction. It gives 1.703 meters is how high you can open up the gate. Open it less than that and the hydraulic jump will run further away, but open it more than that and the hydraulic jump is going to approach and drown the gate. And so now if that is how high the gate is open, think about the gate equation. We know the coefficient of discharge can be calculated by the ratio of the depths, and the width of the channel is the same as the width of the gate in this case. We're going to be solving for y1, and it's going to be in more than one location because it is in the coefficient of contraction term, and it's also in the square root of 2g times y1. So we'll again need to use a numerical solver or Excel in order to find out what will be the depth of the water upstream of the gate. Because we know the flow rate, we don't know the coefficient of discharge in its entirety because that depends on y1. So y1 is the unknown, and it's in multiple, you can see it's in 3 spots in our formula. The depth of the width of the gate, how high the gate is open, square root of 2gh. So the upstream of the gate, the depth will be 1.883 meters. So this is a lengthy process looking at it downstream and working our way upstream. But those are the answers, and unfortunately we have to move on to have enough time left to discuss the beginnings of gradually varying flow. Any questions about the methodology that we would use to determine these 4 depth parameters? Because the 4 things we found was after the jump, before the jump, the gate height, and upstream of the gate. Any questions? Sometimes you'll find the word wide used in a hydraulics problem, and that has a technical significance. What we mean by wide is that it is at least 20 times wider than its depth. And when a channel is wide, that enables us to simplify some of the calculations. For instance, you can calculate the depth for a wide channel using this formula. So Manning's equation for the wide channel is a bit simpler if you know the flow per unit width, lowercase q. And the reason for that is just that when you have so much bottom width that the minuscule amount of wetted perimeter that's on the sides doesn't contribute much. And so effectively what we're saying is if it's really wide, the wetted perimeter is effectively just the bottom width. So that's why we have that assumption when it applies. So when a channel is wide, the hydraulic radius is the depth, and the velocity is the flow per unit width divided by the depth. We're going to skip past this next underflow gate example. We've probably had enough underflow gate stuff for today. Let's talk about gradually varying flow. So at the beginning of open channel flow, we talked about when conditions are steady and uniform. And Manning's equation is used to estimate the depth when conditions are steady and uniform. After that, we talked about specific energy analysis and how that can tell us what will be the depth due to a channel getting wider, narrower, or experiencing vertical obstructions or step down, step up. And so we used specific energy analysis to tell us what would be the depth in a case where conditions are non-uniform. Some of the other cases we've looked at, the hydraulic jump is rapidly varying flow, and flow under gates. We looked at the gate equation. We looked at weirs. Now, gradually varied flow is what happens when two different uniform flow sections are connected, and the water has to go through a subtle transition in depth because of those two sections that it's connecting. And so if you think about a stream that's meandering, that is just experiencing the natural variations in slope that occur because of topography and soil strength and erosion, or the placement of rocks and obstructions in channels can sometimes cause gradual variations in flow. And as the width of a channel changes or the slope of the channel changes, there's changes in velocity. And because there's changes in velocity, then the velocity head will be changing as well. So we're going to go through a couple of different techniques that can allow us to estimate what will be the depth of flow when water is going through these gradual variations. And at the heart of those techniques is just looking to balance the energy loss as the water flows between two sections. So we'll be accounting for changes in energy. And our textbook has a few different causes of gradual variation. So for instance, when water approaches a gate, like if a gate is put into a channel and the water used to be flowing at the normal depth, so here why not just means back when conditions were uniform. So here UF means uniform flow. If uniform flow encounters an underflow gate, then the water is going to pool upstream of that underflow gate in order to obtain enough energy to push the water underneath the gate with sufficient velocity to accommodate the flow rate. So the pooling occurs just to have enough energy to force the water through that narrow opening. But in the section that connects the uniform flow and the gate, there's this gradual increase in depth. So that's gradual varying flow. Another case when water depth will gradually vary is when water is approaching an overflow, when there's a cliff or just some sort of a very steep transition in slope. Then you can see that the water depth is decreasing because as the water goes over that cliff, it's accelerating. And as it accelerates, then the depth is going to be drawing down. So you have the rapid variation in flow depth after the water goes over the cliff. But before the cliff, there's gradual variation in the flow depth. What about if you have two mild slopes that are connected together? So you've got one mild slope and then an even milder slope, meaning shallow. It's not very steep. So the really shallow slope has a larger depth than the slope that was before it. So here you can see it's relatively a little bit steeper, so the depth is less. So there's a gradual transition between those two depths. It's not going through a rapid transition because both of the slopes are mild. So there's not going to be a hydraulic jump or rapidly varying flow. It's just a change that's very gradual in the depth. Or here, in this case, we've got a steep slope. So a steep slope means that when the water comes out from underneath an underflow gate, the water is going to stay supercritical. So the water is supercritical underneath the gate, and then it just gradually transitions to its normal depth, but it's a supercritical normal depth. So it's not going to go through a rapid variation. The gradually varied flow equation is what's integrated in the standard step method and the direct step method that we'll learn next week. It's assuming that the channel that you apply this to is prismatic, meaning that if you have a front view of the channel, that the bottom of the channel is regular. I think we talked about prismatic channels before, where a prismatic channel maybe would be, for example, a trapezoidal channel, where you could mirror it across a center point, and it's the same on the left and on the right. The bottom of the channel is flat. A non-prismatic channel would be if you had a river where the bed varied quite a lot. That's not a prismatic channel, because you couldn't mirror it on the left versus the right, and the bottom of the channel is irregular. So when we apply the gradually varied flow equation, we're assuming that we have a prismatic channel, that we're experiencing steady flow where it's not uniform, but it is steady, meaning that the flow rate's not changing over time. We've got a relatively small bed slope, uniform velocity distribution. Laminar flow conditions means that we're using the kinetic energy correction factor of 1. Hydrostatic pressure distribution as we go downward through the flow, and that the channel roughness between 2 points is constant, that you don't have, for example, a really smooth channel connected to a rough channel. You wouldn't be able to apply the gradually varied flow equation across those two dissimilar surfaces. So what the gradually varied flow equation does is it says this depth is changing gradually. And so what it's going to do is it's going to compare the depth of flow upstream to the depth of flow downstream, and to do a little bit of accounting on the change in velocity, the change in depth. And so it's going to say downstream, like in this illustration, it's deeper. It's deeper downstream. So there's the initial depth here in blue, and then the additional depth in red. And because it's deeper, the velocity is going to be less. So the upstream velocity was v. The downstream velocity would be v plus dv, where dv would be negative because it's going to have reduced velocity downstream since it's got more depth. For the same flow rate, the q upstream and downstream is the same, but because it got deeper downstream, the velocity had to slow down. So we look at the specific energy, both upstream and downstream. And here, remember, specific energy, what we mean by that is the depth plus the velocity head. And if the change in specific energy with respect to depth is 1 minus the Froude number squared, then we're going to look at the different slope of the energy grade line, the different water surface slope, and the bottom of the channel slope. Those three slopes are not parallel to each other like it would be in uniform flow. In uniform flow, where we're using Manning's equation, those three slopes are equal. But they're dissimilar now, and so there's going to be a change of energy with respect to length, where here h, the total energy, reflects the elevation above some datum, the flow depth, and the velocity head. So this is the gradually varied flow equation. And what we're going to do is we're going to try and find out at a certain point how is the depth changing with respect to distance downstream. So this is the governing equation for gradually varying flow in open channels, assuming a prismatic channel with a constant roughness at the bottom, a relatively mild slope. And so given that you have those conditions, then we can integrate this equation between 2 points, and we can find out what is the new depth downstream. So basically what we'll be doing is we'll be saying, I know the depth at either the downstream location or the upstream location. I know the depth somewhere, and I want to know what is the depth, let's just say 50 meters upstream. I'll use this equation to predict what is the new depth at an upstream or downstream location. And what I'll do is I'll be extrapolating the slope of the water surface across that distance between 2 points. Now the slope of the water surface is curved, which is what makes this a bit tricky, is we have to break our numerical integration up into pieces, because if I've got a channel and it's shallow downstream and deeper upstream, like this. This is the water. If I've got y2 and y1, and y1 I don't know. This is a curve, and I can't use a line to approximate the depths, because this is going to be the slope of the change in water depth with respect to distance. And so just looking to the future, the difficulty that we're always going to be playing with is a curved water surface but a flat slope. All right, it's 1:50. We're out of time for today. This is where we'll pick up on Monday. Just remember that this next homework assignment I'll post here in a few minutes, homework number 12, and it's due on Friday of next week.